All right, so thank you for the introduction, Artis. So as Artis mentioned, I'm a professor at the University of Alaska in Anchorage. But one of the things I also do is make many of the color astronomical images that you see in the news. And just to show you a few of the images I've made that maybe you've seen, there's this one. And then also the Eye of God image that came out many years ago. So for many years, I've been making many of the images you see from Kitt Peak, Cerro Tololo, and the Gemini observatories. And so what I want to do with my talk here is to first talk about why we make these images, then how we make the images, and then also answer some questions that people commonly have about them. So why do we make these images? Well, the first and most obvious is to help visualize scientific results. If there's a major discovery and we'd like to do a press release about it, we will often create a color composite image to go along with the press release. Another thing that we often do is make images to demonstrate new technology. So for example, this picture right here shows one of the adaptive optics systems at Gemini Observatory in operation. And finally, a very small fraction of telescope time is set aside specifically for the purpose of just making pretty pictures, just to make images of beautiful objects in space to share with the public. So how do we make these images? Well, to understand that, it helps to understand a little bit about how our eyes make images and how DSLR cameras work as well. So our eyes have detectors in them called cones, and they come in three flavors, the red, green, and blue. And if you've heard of red, green, and blue, or RGB, that's the way in which we can simulate all the different colors that your eyes can see, is by creating different levels of those red, green, and blue. Now, our electronic detectors, our CCD cameras, cannot see color intrinsically. They can only produce black and white images. So the way we create a color image is the same way that your eyes do, and that is that we look at an object through multiple filters. And so the easiest way to do that is to mimic what the eye does and take pictures of an object through red, green, and blue filters. And then we can combine them together to produce a final color composite image. Now, a big difference between the images that your eyes see and the images that our telescopes see is that we can use many different kinds of filter, and we can look at very many different kinds of light. So the cones in your eyes, the S, M, and L cones, the blue, green, and red cones, roughly correspond to blue, green, and red filters. But we have many other kinds of filters that we use in our telescopes. And we can also see other kinds of light. In particular, we also use what are called narrowband filters. And these are filters designed to see specific colors of light produced by different types of gases. So maybe you've heard of hydrogen alpha or oxygen 3. So we often use these filters as well. So we can also make images using more than just 3 filters. This is an example of two color composite images of the dwarf galaxy NGC 6822. The image on the left shows it as it's seen in 3 filters, and the image on the right is how it appears using 8 filters. And in the image on the right, we can see more vivid detail. We can see the nebular regions in the galaxy better, and we can see the colors in the stars better. So what I'd like to do just very quickly is show you how this process works. So I'm going to show you an example of assembling a color composite image of the spiral galaxy M33. And so this is what the galaxy looks like if we look through a blue filter. And this is what the galaxy looks like through a hydrogen alpha filter. And you can see that the galaxy looks very different. So an important thing that's important to teach to your students is that we use these different filters primarily for scientific purposes. And each filter gives us different pieces of information. So the blue filter shows us where the hot blue stars are in the galaxy. And the hydrogen alpha filter shows us where the warm clouds of hydrogen gas are that these stars are forming in. So how do we create the color image? Well, what we do is we take an image through each filter and then assign a different color to each filter. So for the hydrogen alpha, which is a deep reddish color, we give it a red color. And then we use other filters as well. So this is an image taken through an I-band filter, which is infrared light just beyond what our eyes can see. And in this example, I made it orange. And the reason why I did that is because we're already using red for hydrogen alpha. And a good question to ask is, well, how should we use color when we're looking at kinds of light our eyes can't see? And I'll talk about that in just a minute. Next is the R band filter, which I've made yellow. And then the V band, V stands for visible. It's a green filter, which I have made here green. We have the blue filter, and then we also have a U band filter, which sees light in the ultraviolet, which is, again, just above what our eyes can see. So in this example, we take images through 6 filters, and then when we combine them all together, this is the final color composite image. So what's really nice about this image is that it shows you the rich detail inside the galaxy. It shows you the nebula regions, the dusty clouds, and it also shows the colors of the stars. And in this case, this is simply done just to be a pretty picture, but we can use these different filters to learn about the objects we're studying. So we can use the color filters to measure the temperatures of stars or to determine the composition of asteroids and things like that. If we zoom in detail, you can see the colors even better. And so one of the things I think is really cool to teach students about is just all the science that comes out of these colors. So rather than having to fly all the way out to these stars and stick a thermometer in them, we can measure their temperature just simply by looking at their colors. Now, we do the exact same process when we look at other kinds of light beyond the visible spectrum. So this is an example of doing the process in the infrared. So this is a region of the M17 nebula as seen through infrared light with the Gemini observatory telescopes. And when we do infrared light or any other wavelength band, we use the same process. That is, we make the lowest energy form of light a red color, the highest energy form of light blue, and then the colors in between are intermediate. Now in this case, we used 4 bands of infrared light. So we made the lowest energy red, and then green, and then cyan, and then blue. And then the final image that we get combined is this one right here. So while this image is in the infrared and it shows kinds of light that your eyes can't see, it does use the same principles of color. That is, that you would see in the visible. That is, lowest energy is red and the highest energy is blue. Now, when people see these kinds of images, the first question I get 90% of the time is people want to know if this image is real. Of course, we're all familiar with the word Photoshop and how it's become a pejorative for fakery. And so people want to know, are these images they're seeing, are they real? And I love this Calvin and Hobbes cartoon because it actually was written before Photoshop existed. So the questions I most commonly get are, is this what it really looks like? Or are the colors real? Or if I were standing right next to this, is this what it would look like? And in all 3 cases, what people are wanting to know is basically, is the image real? And in particular, is the image real as defined by human vision? And the answer is actually pretty much always no. And I'm going to demonstrate why that is. So this right here is a picture of the Horsehead Nebula that was taken with one of the telescopes on Kitt Peak. And this is a picture as seen by a telescope. Now let's imagine you were to get in a spaceship and fly the 1,000 or so light years out to the Horsehead Nebula. And then once you got there, you looked out one of the portals on your spaceship. What would you see? Well, this is what you would see. You wouldn't see any nebulosity at all. So even though you're much closer to it, you still wouldn't be able to see much of anything. So why is that? Well, there's a variety of reasons. One reason is that surface brightness is constant. It doesn't matter how far away you are from something. So in other words, if you can't see it while you're here on Earth, you still won't be able to see it even if you get much closer. Another thing is that our eyes are famously bad at seeing color in faint light. And in particular, we're really bad at seeing red light, which is why when you go to observatories, you have the red lights around to avoid damaging your dark eye sensitivity. And finally, our eyes can't see all the different kinds of light that are out there. Our eyes can only see a very small portion of the electromagnetic spectrum called visible light. And my co-author and colleague Kim Arkand has a really great analogy for this. And that is, imagine you have a piano in front of you with 88 keys. And imagine you could only hear one of those keys. Imagine you could only hear middle C. Well, that wouldn't be very exciting at all. And that's kind of how it is with our eyes. There's all these different kinds of light that our eyes can't see, but fortunately we can build telescopes that can see those kinds of light. So when we think about telescopes, it's important to remember that telescopes do several important things. And the three main things that telescopes do, the first and the one that people think about the most, is magnify an object, make something that is small appear bigger. And this is what people are usually thinking about. They imagine, like a pair of binoculars, how they can make something far away seem close, and it gives you the same sensation if you were right next to that object. Another thing, though, that telescopes do that people often don't think about is they're designed to collect lots of light and make things that are too faint for our eyes to see bright enough to be detectable. And then finally, to see the kinds of light that our eyes can't see. So the X-rays, the infrared light, and so on. So our eyes are amazing instruments, but they're actually really terrible for astronomy. At their most dilated, they're only about a 1/4 inch wide at the part that collects light. And for comparison, this is the size of the 8-meter mirror in the Gemini Observatory. So what that means is that at any given moment, this mirror is collecting about 1,000,000 times more light than your eye can. And not only that, our telescopes are designed to take long exposures. So we can have the telescope track the night sky, and we can collect light for many hours, whereas our eyes are designed to work like a video camera, where they're only collecting light for about 1/30th of a second before taking the next image. So this allows us to see objects that are billions of times fainter. With telescopes, we can see objects that are billion times fainter than what our eyes can see. So just to illustrate this, this is a picture of the Hubble Extreme Deep Field. If we zoom in, the faintest objects in this picture are, I think, about 10 billion times fainter than what the human eye can see. So an important way to think about it is that telescopes give us superhuman vision. They literally make it possible for us to see things that are invisible to our eyes. So the challenge in making these astronomical images is to translate what the telescope can see into something that your eyes can see. So there's a lot more detail that goes into this, and as Artis mentioned, we did write a book about this called Coloring the Universe, and this book was written by myself and my co-authors Kim Arcand and Megan Watsky at Chandra X-ray Observatory, and this book is based upon the most commonly asked questions when it comes to astronomical images. So not only the ones that I've talked about as far as are the images real, but a lot of the other steps in there. And I'll mention that this book was written in with support from the National Science Foundation to be specifically usable in the classroom. It's not designed to be a textbook, but it is designed to accompany the Coloring the Universe activity that we created that you'll get a chance to do as well. So I hope you'll be interested in picking up a copy. Okay, so I'm going to leave it there. I'm going to end my share screening, and I will be more than happy to answer any questions you might have.
Okay. I was going to say, right now, there's only one question, and that's what software do you use to image and finish pictures?
Yeah, so we use several different pieces of software. First, we use software to process the data, and which software we use depends on what kind of data it is. So for processing optical and infrared data, we use a software package called IRAF, which is best described as user hostile. And we also use Python as well. We're starting to use that more and more. Now, the next step is to convert the data into image formats. And for that, we use a piece of software called FITS Liberator. And what it does is it converts the data files, which are in FITS format, into image files, which are TIFF files. And then finally, we use Photoshop to assemble the color composite image. Now, of course, when people hear the word Photoshop, they start saying, oh, okay, I know what you're up to. But all we do with Photoshop is to take the different color images and combine them into, assign colors to each layer, and then make the final color composite, just like I showed with M33. And then we also do cosmetic cleanup. We remove artifacts from the images that aren't real.
Okay. Next question is, are your color choices you use pretty universally accepted by everyone?
So the colors that we use depend on the types of filters and also the types of data. So if we have broadband filter images, then we always use what's called a chromatic ordering, which is, as I described earlier, the lowest energy light is made red, the highest energy light is made blue, and then we assign colors of the rainbow in between based upon the relative energies. If you're using, excuse me, if you're using narrowband filters, or if you're using filters from multiple wavelengths of light, like if you're combining optical with X-ray, then we will do things a little bit differently. And so we don't have a single color scheme that we use for all of our images, because each image has different data sets from different types of telescopes. So it's basically impossible to have just one single color scheme.
Okay. Another question is, what activities do you want high school kids to learn from the most? Which of the activities?
So the Coloring the Universe activity that we have put together is designed not only to show students how color images are made, but also to show the kinds of science that can be done. So as I mentioned earlier, we can use color to measure physical properties of objects, like the temperatures of stars, or the redshifts of galaxies, or also the compositions of asteroids. So, and that's an important point to make, and that is that people often think these color images are the science, and these color images are visual representations of the science. But when it comes to doing quantitative measurements, we use the actual data itself, not the color images.
Okay. Next question, why the better contrast and detail when you combine 8 filters than when you combine 3?
So how many filters we use depends a lot on the kind of object that we use. And sometimes you can actually do better by having less light. And so that is the purpose of narrowband filters, is to block out most of the light except for very specific colors. And so if we're studying a nebula and we wanted to determine the temperature of the nebula, we would use narrowband filters. But in the case of like a galaxy, which has nebulae and stars in it, then we use both narrowband and broadband filters.
Do you decide the fraction of each color image for specific effects for the image, or do you try to stick to the same fixed mixture for one set of filters?
So as you'll see in the activity, the colors will be balanced differently depending on which filters you have. And when we make our images, we want to use the full spectrum of color, because if you have an image that's just monochromatic, if it's essentially all red or all blue, then you're losing a lot of the information that's contained in the data. So in creating these images, we want to help the brain to interpret the image. And if I had more time to talk about it, I would talk about how the brain uses color to understand what it is seeing. And so we use the hardware inside our brain to help it understand and interpret the images that you're seeing. So for example, most people tend to interpret red things as being hot and blue things as being cold. And so we can use that principle to help convey the temperatures of what's being seen.
Okay, and then I saved this question for the end. Are there ways to translate these color images into something for visually impaired, sound or tactile impairment, or something that we can utilize?
Yes, as a matter of fact, Kim Arkand, my collaborator, and others have created tactile versions of our images.
Mm-hmm.
And another thing that we're working on right now is creating versions of our color images for different kinds of color blindness.
Okay. Are there any other questions? I think the other ones have been answered in the chat line for us.
There was an earlier question about, is there software available compatible with VR?
Uh-huh. That was one that I figured I'd let you field, or if
I'm not sure what that means. Virtual
For
reality?
virtual reality. So our images are not three-dimensional. There are people who have created three-dimensional models based upon our images and what they think they might look like three-dimensionally. So I would imagine it's possible to upload one of those into VR, but I don't know how to do that. I've never done it.
one more has popped in. In determining galaxy distances, how much does galaxy color affect the redshift effect?
So when it comes to figuring out the redshift of a galaxy, you do need to know the star formation history of it as well. And so that's why we use multiple filters to determine that, because you can actually disentangle the star formation history from the redshift of the galaxy by that method.
Another question has come up. How can you access the tactile images you're creating?
That's a good question. So Kim Arkand is the person to ask about that, and I can, if that person who asked the question wants to contact me, I will be happy to help you get in touch with her, and she can get those materials to you.
Okay. Are there any other questions from the floor? Does your book contain info about the brain processing color or V color?
So we do talk about that, yes. We have a chapter devoted to how the brain interprets color to determine things like temperature and depth and motion. So we do talk about that.
All right. Any other questions from the floor? Where can we access the images made for the people who are colorblind?
So those images haven't yet been released, but we're hoping to do so within the next year.
And another question is, could you convert fits to STL files?
I don't know what an STL file is, I have to admit.
Yeah.
I'm sorry.
Jarvis, you want to pop in, turn on your mic and pop in?
I've never heard of that either. Oh, a 3D print file.
Could you convert fits to 3D print file?
Some formats of FITS files might lend themselves to that. There are types of data sets that are data cubes, and so there is a third dimension to it. And so in principle, you could do that, but I've never done that.
Okay. All right. Jarvis, did you have any other comment or any thought?
No, I hope
no,
you enjoy. Oh, go ahead.
Yeah, it's a comment that has turned up when we use the planetarium, because obviously it is fundamentally visual, and we occasionally get audiences and you are thrown a curveball when you say, oh, by the way, we've got a blind student.
Yeah, that's always tough. And there is a comment from Martin that Chandra Images have experimented with the STL files. So sounds like there's some good how did you get into this, Travis?
How did I get into this? So I was a postdoc at Kit Peak at the time that a new wide field imaging camera was being commissioned. And it was an 8K by 8K array, which even by today's standards is pretty impressive. But in 1997, there was nothing else like it. And we wanted to show off the capabilities of the camera. So I had a photography background, so I offered to make some color images to demonstrate the wide field of our new camera. And an important lesson I learned is if you do something once, it's a favor. If you do it twice, it's your job. And so I made a few images, people liked them, and they asked me to keep doing it. And I'm joking, of course, because it's something I love to do, but that's how it all got started more than 20 years ago.
All right. There are no more at this time. So Artis, I'm going to hand this back over to you.
Yeah, and I'd like to thank you again, Travis.
Thank you, Travis.
Excellent presentation. I know a lot of people are very interested in this. Been looking forward to it all week. So I wouldn't be surprised at all if you don't get a few more questions coming your way.
Well, I'll just say to all of you participating, feel free to contact me if you have any questions. And I'll just mention it's a lot of fun. Students really love it. It has a nice creative element to it that students really enjoy.
Travis, do you have an email or a contact that you want to put into the chat?
I will put that
Or
in the
share with us?
chat. Yeah, let me do that now.
Thank
And you
you.
can also, you know, find the speaker page with Travis's information on it. Okay, thank you.
All right, thank you all. I will be leaving now.
Thank you for
So-
being with us, Travis.
Okay, well, you all enjoy the rest of the workshop.
Take
Okay,
care.
appreciate it,
Bye,
Travis.
everyone.
Bye.
Bye.